Okay, hello everybody. This is a video to explain just a couple of examples. So there are two concepts about lifts that confuse people. The first one is that the force weight only acts on the object with that mass. So I think I've done an example before where if you are holding an apple in your hand, you don't feel the weight of the apple. Let me show you on here perhaps. So if this is my hand and this is the apple, then the weight of the apple only acts on the apple. And then the apple feels a normal reaction, a contact force between my hand and the apple. And if the apple has no acceleration, if I'm just holding the apple still, then these reaction forces and the weight forces are balanced. Now if I look at the forces acting on my hand, there is a reaction force down, the reaction force from the apple of my hand, and this is the force that you can feel. It's the sort of sensation you have of what the apple weighs, but it's not the actual weight. You're not actually feeling its weight, because if you lift your hand up, if you push your hand up with the apple in your hand, if you lift it up, then it feels a little bit heavy for a second. It's like when you actually go in a lift, you feel heavier at the start of the journey when the lift is accelerating, and when the lift is decelerating at the end, you feel lighter. Or like when you go over a hill in a car, you're decelerating in a vertical way at the top of the hill, so you feel lighter, you sort of lose your stomach. But the key concept is that, and actually I haven't explained how this isn't falling down, and that's because I'm pushing up somewhere. I maybe got some force from my elbow. I'm pushing up. There's an internal force in my body. But the key concept is that this apple, the weight of the apple is only felt by the apple. Okay, so that will become clear when I do an example in a second with the lifts. The other thing that's important is that the reactions are equal and opposite. Okay, which is, I should cross that out actually. The reactions are equal and opposite. So this reaction here is equal to this reaction here. If you put a baby elephant on a table, the elephant will fall through the table, and that's because the reaction force from the elephant onto the table is too big and the table will snap. But that means the reaction force will reduce and the reaction force pushed up from the table will reduce. But anyway, the reactions are equal and opposite. Let's have a look at a typical example that you'll be asked to do. So, a vertical rope AB has its end B attached to the top of a scale pan. So there's my scale pan, it's maybe got some strings, and I've got some strings attached there. The pan has mass 0.5 kilograms, and there's a brick on that which has mass 1.5 kilograms, and the scale pan is raised vertically upwards with constant acceleration 0.5. So I'm going to put in that the acceleration here is upwards, and it's 0.5 meters per second squared. The rope is modelled as a light inextensible string. Find the tension in the rope, and also find the magnitude of the force exerted on the pan by the brick. So that's the reaction force on the pan by the brick that's on top, so it's pushing down. Okay, so for these questions, what I would ask you to do is to draw a diagram involving all the forces. Okay, after we've done that, we're going to draw a free body diagram just of the forces acting on the lift, and then just on the forces acting on the brick, and then on the forces acting on the system as a whole. So we're taking the whole system to be our free body. Here we're taking the brick to be our free body, and here we're just taking the lift. So we're thinking we've got the lift, the brick's inside it, we're not considering the forces acting on the brick. The brick's an external part of the system. But first of all, let's label all the possible forces we can think of. So we have tension pulling the lift up. We have the weight of the brick. Now I've drawn these forces spread out a little bit just so that we've got enough space to draw them in, but really they should all be about the centre so there's no moments. The brick is 1.5 kilograms, so that's 1.5 g. We also have the weight of the lift, which is 0.5 g. So the weight of the lift, I'm going to put that here, 0.5 G. And then we also have the reaction force pushing the brick up. So it's the reaction force of the lift on the brick. So let's call that reaction here. And then we have an equal opposite reaction of the brick on the lift, so pushing the lift down. And those are all our forces. Okay, now if we just look at what the forces are acting on the lift, we have the tension pulling the lift up, we have the weight which is acting on the lift, and we also have the reaction from the brick. So we have a reaction force pushing down. If we now look at the brick can feel its own weight, so it can feel the 1.5 G. The weight is acting on the brick. And the brick also feels a reaction from the lift, so it's being pushed up from the lift. There are no other forces acting on that brick. Okay, if you imagine yourself as the brick, you're stood in a lift, you can feel your own weight pulling you down, and the floor of the lift is pushing you up. Okay, now onto the system as a whole. And now onto the system as a whole. Here, now that we've done this, the reaction forces are internal forces and they balance each other out. So you just have the tension pulling the lift up, and you have the combined weight of the lift and the brick, which is 1.5 plus 0.5 G, which is 2G. So we're now going to use these three equations to find our two unknowns. Okay, so I can just use this one to find tension, I can just use this one to find the normal reaction. In other questions you might need to use this third one and make a simultaneous equation out of a few, especially when there's an unknown mass. But for this one it's pretty straightforward, it's just this and this. Now remember, the acceleration of 0.5, everything's accelerating up at 0.5 meters per second squared. Okay, so it's not a case that R just equals 1.5 G. Okay, in fact, if we look at the, so let's resolve the brick taken up to be positive, we know that the resultant force equals mass times acceleration. The resultant force is R, take away 1.5 G. And that equals the mass. The mass of the brick is 1.5, so it's 1.5 times by the acceleration, which is 0.5. Okay, so R is just 1.5 G. What is 1.5 G? 1.5 times 9.8, 14.7. So it's just 14.7 plus half of 1.5, so 0.75. So my answer is 15.45 newtons. Okay. Now if I do the exact same thing on the lift, I'll resolve the lift, take it up to be positive, the resultant force equals mass times acceleration. The resultant force is T take away 2G. T take away 2G, and that equals the mass of the lift, the mass of the whole system. I'm taking the whole system here, I'm looking at the whole system. The mass of the whole system is 2, so it's 2 times by an acceleration of 0.5. So the tension in the system is 2G, which is 19.6, plus 2 times a half, which is 1. So the tension in the system is 20.6 newtons. Okay, so those are our two answers. Now this question asks us just for the magnitude of this force. We've actually worked out the force exerted on the brick by the pan. We haven't worked out the force exerted by the on the pan by the brick. The force on the pan by the brick is actually this force, but because they're equal and opposite, this is actually 15.45. But if the question asks us for the magnitude and direction, we would have to say that the force is downwards, and the tension in the rope is 20.6. And we could, if we want to, just check that for the lift on its own. So we're saying that 20.6 take away R, which is 15.45, take away 0.5 g, which is half a g, 4.9. And that's going to equal the mass, which is 0.5, times by the acceleration, which is 0.5. So is that true? 20.6 take away 15.45 take away 4.9 equals a quarter, 0.25. So we have got our answer correct.